Welcome to Pharmaceutical Calculations, a Conceptual Approach, Lesson 10, Dilutions. Now this is the first part of 2 lectures. In Lesson 11 we're going to see dilutions and concentrations of pharmaceutical mixtures, but in this today's lecture we are going to examine only dilutions using the concept of mass balance preservation. So our objectives for today is to explain the concept of mass preservation in the process of dilution and create mathematical expressions out of this concept and use them to calculate drug concentration of diluted pharmaceutical solutions. Now there are 2 ways to perform dilutions. The first one is by varying the volume of the solution while keeping the mass of the drug constant, and this is the common method used in compounding preparations. And the second one is by varying the amount of drug while keeping the volume of the solution constant. And this second method of diluting a mixture is used commonly in quantitative drug analysis and in research. However, in most of the sciences, chemistry, biology, physics, pharmaceutics, you need to know both methods. Both of them are used. Now, how do we calculate the amount of drug in solution? Well, we have described this equation, this fundamental equation in lesson 8 and 9. And if you solve for the mass equal to the concentration times volume, that is actually the way to calculate the mass of the drug in solution. Let us take a look of the physical process involved in a dilution process. To the left, I have my stock solution. I have dissolved 50 milligrams of a drug in 50 mLs of volume, and the concentration using the fundamental equation mass of the V is 50 over 50, which is 1. Then I add more water, 200 ml of water approximately, and I end up with a 250 ml of volume. And of course the concentration using the same equation as for 1, the final concentration, let's say, is going to be 50 milligrams over 250 ml of solution, and that would be 0.2. Okay. So during the process of dilution with this method, the only parameter that is kept constant, and here the I stands for initial and the F stands for the final state, is the mass, as you can see here. I didn't add any drug. I've added more volume, and as a result, the concentration of the drug is reduced. Now, since the initial mass of the drug is the same as the final mass of the drug, and we know that mass is equal to C times V, I come up with this equation here. C1V1 is equal to C2V2, and you can use any version to calculate changes in drug concentration during dilution, but always have in mind that the VF or the V2 includes the initial volume. This is very, very important for you to remember. So let us take a look of example 5.1. It's asking you to calculate the concentration resulting from diluting the initial solution shown in figure 5.1, which was 50 milligrams of mass of the drug and 50 ml of volume, when it is diluted to a final volume of 100 ml, not 250 ml. Now there are 2 ways to do that. Now of course C1 is equal to mass 1 over V1, and that's why it's 1 over there. You can just go ahead and use our equation based on mass preservation of the drug in the 2 states before and after dilution. So for C2 and substitute for the right numbers there. 1 is the concentration, 50 ml is the initial volume, and 100 ml is the final volume, and you're going to end up with that. Alternatively, you could have used, starting from, let's say here, during the process of dilution, the mass of the drug is equal to the mass in the initial state is equal to the mass of the drug in the final state, and this is equal to C2 times V2. Therefore, the C2 is equal to the mass of the drug mass 1 over V2, and that's equal to 50 milligrams, and the V2 is 100 ml. So you end up with the same answer. This is the analytical way. Either way is fine, of course, because it is essentially the same concept. The concept of mass preservation during the process of dilution. Let us now take a look of example 5.2. It's asking you to determine the concentration of the drug contained in 10 ml volume of the initial solution, shown in figure 5.1. So the question here, are these 10 mLs diluted? No. If it is not diluted, then the concentration in that portion of solution taken from the stock solution is exactly the same as that in stock solution, because it is a homogeneous mixture. Any aliquot you take from that solution will contain the same concentration. If you take a bigger volume than 10 ml, will proportionally contain bigger amount of drug because the concentration is kept constant. If you take a smaller aliquot, smaller than 10 ml, it will contain proportionally less drug because the concentration is constant throughout the solution. That's why it's called homogeneous mixture. And of course, the way we calculate the concentration of the drug in that solution, we have 50 milligrams in 50 ml. Since the solution is homogeneous, in 10 ml, how much? And you get 10 milligrams, and that's the same concentration. What do you think is the drug concentration in 2 ml, 5 ml, 24.978, whatever you want to say, of the initial solution? As we said, since there is no dilution, it's always going to be equal to 1 milligram per ml. What is the concentration of drug in the dose? That's a question that many students get confused. And the answer here is that if the dose is taken from the original stock solution, the original container of the drug without dilution, then the concentration is the same as that in the original solution. Let us now take a look of example 5.3. It's asking you to calculate the concentration of the corticosteroid ointment resulting from mixing 10 grams of 10% hydrocortisone ointment with 40 grams of petrolatum album. So two things over here. First of all, this 10%, because it's for the ointment, is a semi-solid, the units are weight per weight. Now, for practice purposes, exam practice purposes, that's the rule we follow. But if you are working in a compounding lab or in a formulation department in a pharmaceutical industry or in research, you better make sure that the information about the units of the ointment is given to you explicitly. Do not assume that is weight per weight. Now, the second important point here is that this petrolatum album is Vaseline, and basically there is no drug added. So essentially, we perform dilution of an ointment here by adding more of the base, which is the Vaseline or petrolatum album. Now, we can use the same concentration, the same equation, C1V1 equals to C2V2, but because here we have an ointment which is solid, we can rephrase, or we can rewrite this as C1 capital M1 is equal to C2 capital M2. Now these M's, M capital is the amount or the mass of the ointment, not of the drug. So now we can solve for C2, that's C1 times M1 over M2. Exactly now, the word of caution that we discussed before, this M2 is the final mass of the ointment, and it includes the initial mass. So that would be 10 plus 40, which is equal to 50 grams. So now I have C1 is 10% weight per weight, mass 1 is 10 grams of ointment, and the final mass of the ointment, when you add 40 grams of petrolatum, is 50 grams. So then I have 10 over 5, which is 2. So 2% weight per weight is my final concentration. So all of these explanations of definitions of units are written here, and you can see here clearly explained for you that M capital is the mass of drug, and of course M lower letters R is the mass of drug. M capital is the mass of mixture, I'm sorry. So and when you proceed applying this equation, you get your answer. Now that's why I make sure that you understand that the difference between the M capital, that's the mass of the ointment, between the mass of the drug from the mass. Now alternatively, of course, since the mass preservation is M1 equals to M2, right? So here I have M1 equals to M2, or Mi equals to Mf, but Mi, Ci, Mi, and Mf is equal to Cf, Mf. This Cf could be equal to Mi is equal to Mi over Mf, M initial over M final. So if I use numbers, this C2 would be equal to the mass of the drug in the initial state, M1, over the mass of the ointment in the final state, over capital M, okay, capital M. So that would be 1 gram over 50 grams, which is 0.2 or 0.02 or 2% weight per weight. If you multiply by A100, you get that. Okay. Finally, let's go to example 5.4, which is the most challenging. Let us take a look of the description here. Calculate the concentration of drug X in 4 fluid ounces of solution if 1 teaspoonful of this solution diluted 250 ml resulted in 0.005% weight per volume of drug X. How many grams of drug are there in 1 teaspoonful? This is perhaps representing the dose. And how many are there in 4 fluid ounces of solution? So the first thing to do here is to read and understand the question and draw a diagram. A sketch helps you a lot. So let us first make this phrasing simpler. So we're taking 1 teaspoonful from the original solution, no dilution, right? You just take 1 teaspoonful from the original solution, and then you dilute it to 250 ml. The concentration of that 250 ml is 0.005% weight per volume. What is the drug concentration in the original container? So let's draw a schematic here. So this is my original container. I'm taking 1 teaspoonful, which is 5 ml, and I'm diluting it to 250 ml, and the resultant concentration is 0.005% weight per volume. What is the concentration? So now this is easy because we have preservation of mass, and that would be the concentration. C1 would be the concentration of the drug in the 1 teaspoonful. So using the numbers now, our numbers, 0.005% is C2, V2 is 250, V1 is 5 ml, the 1 teaspoonful, and that's my C1. Now, since there is no dilution from the teaspoonful to the original 4 fluid ounces bottle, C1 is going to be the same as the concentration of the drug in the bottle. Simple as that. The way I calculate, of course, the amount of drug in 1 teaspoonful, I multiply the concentration in the teaspoonful, which is 0.25 grams per 100 ml, times 5 ml is the volume of 1 teaspoonful, and I get 12.5 milligrams. The concentration of the drug in the bottle, we can calculate the same way. That's my concentration, times the volume of 4 fluid ounces, so that's basically 4 times 29.57 ml, and that's the one, 18.28, and you get 295.7 milligrams. And it does make sense because you have a proportionally larger volume as compared to 1 teaspoonful, and you of course get proportionally more drug, since the concentration of the drug in the bottle, in the original bottle, and in the teaspoonful, since there is no dilution, is constant. Now I have included 4 exercises for you to practice. The most challenging, of course, is the last one here. I do encourage you to practice all of them. Shouldn't take you a long time, maybe around half an hour. And at this point, I would like to thank you for your attention. Until next time.